Okay guys, so let's start the session. I hope there are many people will join soon, and welcome to all of you once again. And today our lecture 3, in which we will study about the antenna design procedure. Okay, first let me know whether everyone are able to see the screen and hear my voice, can listen my voice.
Yes, it's clear.
Okay. Okay, so on the third day we will study about the antenna design procedure. Okay, and some other basic tools of the antenna. Okay, so as I described in the previous lecture, you need to follow these steps. Okay. Okay, you can write any frequency range, okay, to calculate E field, H field, or far field. Okay, if you set these range. Okay, so let's start with the antenna designing procedure first. Okay, okay, let's first design the substrate of the antenna. Okay, you know, uh, there are two layers in the antenna. One is the conductive layer and the other layer is the insulator. Okay, so all substrates are like insulators. Okay, so here is the substrate. Sorry, let me uh, okay, now you can see the local axis, and now you can write here substrate, and u minimum, as I told in the previous lecture, u minimum is the opposite side and u maximum is the right side. Okay, so I need half of the substrate on the left side. Okay, minus ws by 2, and I need half of the substrate on the right side. Okay, in this way. Okay, so now v minimum is the downward direction. Okay, and v maximum is the upward direction. Okay, wait for a minute, some people are saying uh, okay, I was talking about this one. V minimum is in the downward direction. Okay, and v maximum in the upward direction. So you are writing here length of the substrate, okay, by 2, and length of the substrate. Okay, and you can insert any values here, like for this width I write here 30 millimeter. Okay, and for the length I write here 45 millimeter. Okay, and you can see here. Okay, now I write the TS, or you TS means thickness of the substrate, or you can also write HS, height of the substrate. Okay, so it's up to you. Click on the preview, then it will ask you what should be the height of the substrate. Okay, so 1.6 is the millimeter is the height of the substrate. Okay, and you can see here there are so many materials. Okay, and let me discuss about one of them, few of them I mean. Let's first discuss about the FR4. Okay, now you can see there are many FR4 here, so you need to choose FR4 lossy. Okay, because in practical use it will be lossy material. Okay, and to know the properties of any material, you can see here. Okay, can you see here? You need to know the epsilon value. Okay, and the electrical tendency. Okay, or you can say it means the loss tangent. Okay, and then the thermal conductivity. Okay, you need to know these values. Okay, and for the Roger, and you can see every material has different materials, I mean properties. Okay, like for Roger you can see here. Okay, and keep in your mind this is the epsilon. Okay, and epsilon is inversely proportional to the operating frequency. Okay, relative permittivity or epsilon is inversely proportional to the frequency. Okay, so it means if your epsilon value increases, then your frequency will decrease. What does it mean? Suppose you have a substrate of epsilon, like you have FR4 substrate, okay, that has a epsilon value of 4.3. okay, like you have a FR4, okay, and it has epsilon value of 4.3, and suppose it is resonating at 2.5 gigahertz. Okay, 2.5 gigahertz. Okay, and you have any other substrate that is Roger. Okay, and it has the epsilon value of 6.5. okay, it means then if you have higher epsilon value, then your frequency will decrease. Maybe it will work at 900 megahertz. okay, not much difference, but I mean it can be lower than, okay, 2.5, or it can be 1.5 gigahertz. okay, it depends on your structure, okay, and the size of your antenna. Just keep in your mind this relation. okay, epsilon value is inversely proportional to the frequency. okay, let me complete the relation. Mm, as you know, we have the formula.
Sorry, Mr. Rehab, Mr. Sarosh.
Yes,
Can you please repeat the last?
this one.
Yes.
Okay, I was explaining that you have FR4 substrate, okay, and you know these are the properties of the any material. okay, you can see, if you can change, you can see all have different properties. okay, so I am first talking about the FR4 substrate, and you need to choose the FR4 lossy, because this is the lossy material, and in practical use it will be also a lossy material. okay, so you can see here we need to know these three things: the epsilon value, okay, electrical tendency, that is called what we say, loss tangent, okay, and the thermal conductivity. okay, and you, yes,
So we must choose always lossy, not lossy free.
yes, always choose lossy, because if you want to fabricate the design, if you want to fabricate the design later on, okay, because all the materials are lossy material in I mean in practical. okay, but in simulation
Okay.
you can use lossy free if you want.
Okay.
okay,
And we can choose FR for range for frequency.
okay, yes, okay, let me explain this one too.
Okay.
okay, first know this one. FR4 has the relative permittivity of 4.3. okay, and suppose I am using Roger, that has the epsilon value of 6.5. okay, and just keep in your mind this relation: relative permittivity is inversely proportional to the frequency. okay, if you have, suppose, FR4 substrate, and it has the relative permittivity of 4.3, and suppose it is resonating at 2.5 gigahertz, and then if you change the material, like if you change the material Roger material, and it has the relative permittivity of 6.5, then it maybe works at 900 megahertz, it maybe works at 1.5 gigahertz. okay, it depends on your structure. okay, so that's why I am saying this one. okay, now what was I going to explain here? Okay, what question did you ask me? Can you repeat your second question?
No, it's clear.
Okay.
Okay, thank you.
Yes, and one more thing. FR4 is works well up to 20 gigahertz frequency. Okay,
Okay.
this one. If you are using FR4, then it will work perfectly at up to 20 gigahertz. But if you want to increase your frequency range, okay, then you need to use Roger material. Okay, Roger.
What the reason?
Actually FR4 is the lossy material, okay, and it is what we say, it has the thermal conductivity. Okay, if you suppose like an example of an apple, okay, if you keep your apple in the open atmosphere, it will discard after few days. Okay, like this FR4 will not work for a longer time. Okay, that's why it may
Okay,
affect by the atmosphere. That's why Roger are just like a sheet of the paper. Okay, that's why they will not discard.
okay.
Okay.
So, Mr. Saroush, if I need to create a new material, I need three parameters: epsilon r and tan
Yes,
delta,
yes,
and also the thermal conductivity, at least, yeah.
yes. I will explain now. Okay, okay, I was just explaining this one. Different there are many different materials. Okay, you can see here, you can use any material here. There are a lot of materials. You have to choose that material that is easily available in your country or in your place where you can fabricate. Okay, so you need to choose only the available material, not only to choose any material that is not available later on. Okay, so you just keep in your mind before starting your design. Okay, and FR4 is not a and one more thing, FR4 is not a flexible material. If you are using uh, thickness of 1.6 millimeter, okay, or 3.2 or 3.2, okay, it is not flexible at this millimeter. Okay, but if you are using 0.8 millimeter, then it is flexible. Okay, not much flexible, but somewhat you can say it is flexible. Okay, okay, so FR4 also is a very cheap material. Okay, rather than Rogers are costly materials. Okay, so most of the people like to use FR4 substrate. Okay, okay, now I click on it. Okay, now you can see here this is FR4 substrate. Okay, the other thing you asked me about the new material. Yes, you can see you can create a new material here. Okay, if you know the values, okay, like this, you know, if suppose if you know the value of epsilon, you can write here epsilon. It is mostly 1, and the electrical conduct, you can write two values here. Okay, any of two. You can write electrical conductivity, you can write loss tangent if you know. Okay, you can write here like this. Okay, and click OK, and you can see your new material is now created. So this is your new material. If you want to check the properties, you just click on the substrate and you can see here, okay, the values you have put here. Okay,
Mr. Saroush, I want to ask you something. I measured a new material one month ago, and I have a real value and imaginary value for epsilon. At this time, I need to put the real value or the absolute value.
of what? Of you have
the machine. Yes, the machine which I measure, the new material I measure both the real value of epsilon r and imaginary value for the epsilon r. I need to take the real value or I can take the absolute, just the square root of the.
Yes, absolute value. You mean you need to take both values. Okay, like you use the formula real value square plus imaginary value and then under root. Okay, like you can calculate the magnitude of that values. Okay, okay, now let's move further. Okay, and today is just to learn the antenna design procedure and its feeding methods and other things. Okay, and these tools. Okay, and from tomorrow we will start following the research paper and we will design properly. Okay, So today lecture is just to learn the antenna design procedure, okay. And in antenna design procedure there three things you keep in your mind, okay. The first thing is the resonator, okay, that is on the front side of the substrate, okay. The other thing is the non-conductive layer, that is the substrate, okay, that is insulator. And the third layer will be a ground plane, okay. Ground plane can be on behind the substrate, or ground plane can be in front of the substrate, okay. Like the let me explain what I mean, okay. I am going to design a feed line first, okay. Feed line here in order to excite the antenna, okay. So I write here WF by 2 and LF, okay. And you can write here TP. What is this person?
Suraj,
Yes.
This field line should be started from the ground plane edge or just a patch edge?
Yes, it should be start from the edge, or if you are using waveguide port, okay, this one. It depends on which feeding method you will use, okay. Then you have to design the field line like this, okay. This I am talking about here a patch antenna, okay, simple patch antenna. Wait a minute. Hello Mr. Chinese, what is your name please? That have joined the recently.
Chinese?
No, I'm not asking you. Just turn off your micro. The person who joined recently, I don't know, he written a Chinese name. I don't know who is he.
Oh, my name is Silpa.
What your name? You can write here.
Silpa. Yeah.
Because you need to every person need to write your name as you have registered, okay, so that I can yes.
Silpa from Korea.
Okay, welcome to Siho Park, you mean, okay.
Yeah.
Okay. Okay, now let's go to the field line. Okay, I will show you how can we design different field lines, okay, here. Because I will explain each and everything, okay, because in the research people do not follow any previous research, or like they just if you create any new shape like or any new technique, okay, then you are able to publish a paper, okay. So you need, but it must be true, okay. Like if I am going to design a field line, okay, here first let me explain from simple things. And you can write here TP, thickness of the patch, okay. And you know copper is a conductive material, so you need to copper, okay. There are two types of copper here. You can use any copper, okay. Some people like to use pure copper, some people like to use any copper, okay. And there is no much difference in the properties, you can see here, okay. But I mostly use here copper anneal, or some people like to use PEC, perfect electric conductor, okay, this one. Okay, now the standard thickness of the copper are of three types. Copper are available in three types of thickness. It is available in let me write here.
Sorry, Mr. Ahmed.
Yes, please.
What difference between copper and PEC?
I told you that one is the same as the copper, PEPEC, okay. That one is the perfect electric conductor that conducts electricity perfectly, okay. While the other material such as copper, the same as PEC, okay. Because there are also electrical conductivity, because it depends on your availability, okay. Like in some of my design I use PEC because of the availability of the PEC material, okay. And in some of the most of the design use copper, okay. And if you see any sheet that will be covered with the copper. Okay, so that's why you mostly use here copper anneal or copper pure. Okay,
so you mean I can choose copper or PET?
yes, it's up to you, depend on availability. It will not disturb your results much. Okay,
okay, thank you.
okay, what I was going to explain. Okay, yes, I was talking about the thickness of the patch. Okay, copper, sorry. So mostly copper thickness are available at this material. Okay, thickness available, I mean standard thickness. Okay, and this one, and this one. Okay, so most widely used thickness is this one. Okay, if you are using at CST, but in HFSS users use 0 millimeter thickness. Okay, but you need to use this one. Okay, this one. So click on the preview and you need to write the first width of the field line. I write here 1.5. Okay, and length of this width 5. Okay, and thickness of the copper is 0.035. Okay, and you can see here this is your field line, and you can extend your field line here. Okay, by typing here 10 millimeter. Okay, okay, this one like this. Okay, okay, now I want to create a shape of the resonator. Okay, how can I make this? Let me explain with the simple one. Okay, I am going to make a simple patch minus WP by 2, width of the patch. Okay, and length of the patch by 2 in TP. Okay, okay, now click OK. Now you have to connect this patch with the field line. Okay, now you can extend here. Okay, now you need to go down. Okay, so this is your patch. Okay, in the other way you can directly do like this. Let me delete this. If you don't know the values, you can directly write the values here. Okay, you can write in this way. Okay, and this one is the V minimum in the downward direction, so you need to reduce the V minimum value. Okay, like this. Okay, now you can see both are connected. Okay, now I write here TP, sorry. Okay, so this is your radiator. Okay, the patch and the field line and the substrate. Okay, now we have missing one thing, the ground plane. Okay, so we need a ground plane on its back. Okay, you need to know the values of the length and width of the substrate. Okay, I don't know why the width of the is not visible. In most of the cases it is visible, I don't know why. Okay, okay, now there is another method to design a ground plane or a full copper like this. You need to select the whole surface. Okay, just go to the brick option and write here the thickness. Okay, TP, and click OK. You can see, click OK, and you can see here, and then remove the clear pics. Okay, now you can see you have a complete ground plane. Okay, this is complete ground plane, and this is patch antenna, simple patch antenna. Okay, okay, now you need to excite the antenna. Okay, you need to use a waveguide port here. Okay, you need to first pick this point. Okay, the edge of the field line. Okay, now you need to go to the waveguide port. Okay, now you don't know what should be the values of the waveguide port. Okay, so you can go to the home, go to the macros. Okay, go to the solver and go to the ports, and then click on the calculate port extension. Okay, now click calculate and construct port from pitch point. Okay, and you can see there is a port. Okay, so I will explain more about this waveguide port. Let me simulate this design and let's check the results. Okay, so you can see here T, there is a small t here, so it means time domain solver. Okay, so you click on it and okay, let me simulate this one, then I will explain each and everything.
Mr. Ahmed.
Yes, please.
You hear me?
What?
I can't hear you clear.
I did not understand what you mean. There is a loud.
Mr. Ahmed, if I reduce the size of the ports, the result will be changed?
Yes, I'm going to show you everything. Don't worry about that.
Okay.
Let me simulate this one, then I will explain what will be the effect of the results if you increase or decrease or use other ports. Okay, I will explain everything. Did you watch the previous lectures, all of you? Everything is clear? The main target of this training course is to target a good research papers and to learn different antenna types. Okay, I will once we start the proper antenna design process, I mean the other types, okay, like these types, single, multi, wideband, flexible, then we will discuss in depth, okay, each and everything to target good journals. Okay, because I will tell you in the next lectures some shortcuts to write research papers, okay, and to publish research paper, because I have a record. I have published more than 45 research papers in just 1 year. Okay, and 6 book chapters. Okay, let us wait.
In this excitation, did you use planar wave or what?
What? This is waveguide, simple waveguide port, not a planar wave. You can see this is another port.
I mean for the excitation signal.
Yes, we will see here once let the simulation will complete. Okay, now our simulation is complete, has been done, and you need to see the S11. Okay, you can see this is resonating at how you can see this is resonating at this point, because the reflection coefficient value must be below minus 10 dB. Okay, so you can see here this is minus 10 dB. Okay, this is a minus 10 dB line. Okay, or you can have a marker here. I think there is no, yes, this one. Okay, at minus 10 dB you can see this curve is above minus 10 dB, so it means your antenna is not resonating at 2.5. okay, so now see the next one, it is resonating at 5 point okay, you can see it is resonating at 5.04 dB, and the reflection coefficient value is minus 29.684 dB. okay, and here you can see the line impedance or reference impedance, that is not 50 ohm. okay, so what will you do to set at 50 ohm? okay, there are two types of connector available. One connector is available for 50 ohm. okay, that is standard, and 98% people use 50 ohm connectors. okay, the other connector is available of 73 ohm. okay, very less people use this type of connectors. okay, so that's why we need to set the impedance at 50 ohm. okay, so I will tell you how can we calculate. okay, the other is the efficiency. okay, one is the radiation efficiency. okay, that is only of the antenna, and the total efficiency that includes the environment, okay, around the antenna, and you need to calculate it in the linear. okay, and you can see here, like if your antenna is resonating at 5.04 like this here, your efficiency is multiply this one with 100. okay, and you can see it is 4.7% efficiency. okay, that is very low. okay, and at 2 you can see here it is 9%. okay, so still it is very low. And the radiation efficiency, you can see it is 18%, 18.6%. okay, the radiation efficiency, I am talking about only the antenna, I'm not including the environment. okay, and here it will have 55%. okay, and you can see the big difference. okay, they must be closer to each other. okay, you can see they are very they have very far difference between them. They must be linked with each other, or must be very near to each other. okay, so they are very far. okay, so you can see our line impedance is not at 50 ohm. okay, there are two to three ways to set at 50 ohm. okay, okay, one more thing, if you decrease the port size, like you ask me like this one. okay, you have the width and you have the length. okay, if you, the port is also inversely proportional to the frequency. okay, if you reduce the port, then your frequency will increase. Frequency will increase means your frequency will not resonate at 5.04 gigahertz. It will maybe resonate at 6 gigahertz. okay, if you reduce the size of the port. okay, so to set at 50 ohm, you need to do the following steps. okay, first let me discuss about some of these things. You have a far field here. I did not call the operating band, like I have a 5.04 gigahertz. I did not call this one. okay, so you can monitor the call and you can check the results. okay, okay, you can see this is the radiation pattern. okay, far field directivity okay, in this case we have a far field, we have directivity, we have gain, we have realized gain, we have E field, we have E pattern, H field, or power flow. okay, so first we have a directivity means the gain of the directivity only of the antenna. okay, and it is in dBi. okay, so how can we first let me remove the other ones view. okay, now you can see the main lobe magnitude. This is the main lobe. okay, and this is the back lobe. Okay, so in antenna case there should be no back lobe. Okay, there should be a main lobe that may be wider, okay, or that may be in like, or the pattern can be a circle. Okay, if you have a circular pattern, then it can be called omnidirectional pattern, that your antenna is working in every plane, okay, at every angle. Okay, but if you have a directional pattern, then it must be on the upside, okay, like this. Okay, and there should be no back lobe. Okay, and you can see that the directivity of the antenna is 3.5 dBi. Okay, and you can see here it is in dBi. Okay, if you see here gain, it will be in dB. Okay, and the realized gain and the the gain, IEEE gain and the realized gain mostly should be very close to each other, like the radiation efficiency and the total efficiency. Okay, realized gain also include the environment, okay, as I told you in the total efficiency. Okay, but the IEEE gain is the gain of the antenna, okay, in free space. Okay, so to set the 50 ohm you can do following steps. Okay, and also you can see the values here, what the values here. Okay, okay, let me delete this port and explain how can we set 50 ohm, okay, impedance. Okay, there in CST there are two to three ways to set the impedance at 50 ohm. Okay, one is the difficult and the other one is the simplest way. Okay, like you can use pick the points of the field line. Okay, I pick the point of the field line, and then I pick the point of the ground plane. Okay, like this. Okay, we have 2 points. Okay, and in the simulation you can use discrete port. Okay, discrete port, if you write here 50 ohm, then it will set at 50 ohm. Okay, 50 ohm, and if you click OK, then you can see the port here, it is exact 50 ohm. Okay, now I simulate and check results. What is the difference in the results if we set at 50 ohm? Okay, in most of the cases I mean the simulation and in the measurement results, some results are not very close to each other, because people do not care about the reference or line impedance. Maybe they simulate 64 ohm with 64 ohm port, or but in the in the practical use in the fabrication they use 50 ohm ports. That's why there is a sometimes big difference in the simulation and measurements. Okay, so you need, while designing your antenna, you must know the reference impedance, okay, or line impedance. It must be set at 50 ohm. Okay, so that your results will be closer to each other. This is the first way. You can use the discrete port to set at 50 ohm. Okay, and the other way I will also tell you in. If you want to use waveguide port and want to set at 50 ohm, I will tell you in a while. Okay, let me complete this simulation.
Mr. Sarosh.
Yes, please.
What do you advise or recommend us for port? What type of port I must choose?
Okay, I will tell you. I advise all types of port, or you can use any port you want. Okay, let me explain. Okay, if you want to use discrete port, then it will also okay for you with 50 ohm. Okay, but if you want to waveguide port, then it is also okay. Okay, to set at 50 ohm, I will tell you how to set the waveguide port at 50 ohm. Okay.
Because I don't want I get big difference between result when I fabricate antenna. So what I choose waveguide port or discrete port or lambda port?
You cannot use lumped port as a DC. Okay, in HFSS we call it lumped port, but in CST we do not call it as a port. Okay, this is for we use lumped port lumped elements, okay. In the case of the, if you want to solder any lumped element like capacitor, resistor, inductor, okay, I will tell you how can we use lumped port lumped element. We use only three, okay: waveguide port, discrete port, and lumped elements, okay. So you can see now the reference impedance is exact at 50 ohm, okay. And you can see the difference in the results. At first it was not resonating at 2.5, but now when you set 50 ohm, it is at working at 2.5, okay. And in this case you can see now it is not at 5.04, okay, so it is at 4.932, okay. So this is with the this port, okay. This is called discrete port, okay. You can see here. This is also advisable, you can use if you want, okay. But if you want to use a waveguide port with 50 ohm, then you can also use, okay. Okay, let me
choose coaxial port.
Yes, you can also use coaxial port, I mean the connector, okay.
Can you explain the S parameter, please?
Okay, let me explain this one first. Waveguide port with 50 ohm, then I will explain S parameters. Okay, now I click again, okay. Now you need to use the waveguide port, okay. So because the purpose of this waveguide port is to set at 50. If you have a port 50 at 50 ohm, okay, then do not care about the size of the port, okay. You can use, okay, you can use this one that I have described earlier. You can use here solver, okay. Go to the ports, and then first you need to calculate this port, okay. Just draw a port here like this, okay. Then when you go to the simulation, okay, like this, you can see here as parameter setting, okay. So you need to click on it and you can write the impedance here, okay. So it will set at 50 ohm even if you are using waveguide port, okay. And now this port is at 50 ohm, okay. When you simulate it, you can see it will be at 50 ohm. So in this way, if you want to use waveguide port, then you need to do setting in the time domain solver, okay. You need to click on the 50 ohm, normalize to 50 ohm.
And for this case, the result will change?
No, the discrete port results that I have shown you, the discrete port, okay, and the waveguide port with 50 ohm will be the same.
Okay, okay.
Mr. Sarouj, I want to ask you, for using the discrete port, I need to connect the second edge of the feed line and also the first edge of the ground.
Yes, yeah? Yes. I will also show you if you want to use a coaxial.
If you need to zoom this area.
This.
The second edge, yeah.
Yes, this is the edge, like this edge, second edge, this one, okay, and the edge of the ground, okay, this one, okay. I will also show you how to connect the discrete port if you want to use the coaxial probe, okay.
Thank you.
Because this is with the waveguide port, okay, for the connectors.
Excuse me, Ahmed.
Yes, please.
Is there any difference between IEEE gain and realized gain? Can you please tell about that?
Yes, I explained earlier. As I explained in the radiation efficiency and the total efficiency, the radiation efficiency only is the efficiency of the antenna, okay, excluding the environment, okay, or while total efficiency include the environment around the antenna, okay. Similar in the same way, the gain IEEE gain and the realized gain has the same difference, like realized gain tell about the gain of the antenna including the environment around it, okay, while the IEEE gain also tell the gain of the only of the antenna, not including the environment, okay.
Okay, okay.
So you need to check, if you need to check first the while you are using the I will show you, let me complete this, then I will show you the graph here to better explain. Okay, you can see here there is no much big difference about the discrete port and the waveguide port, okay. So I suggest you to you can use any port here, okay, discrete port or waveguide port, and also check the reference impedance, it is at 50 ohm, okay. Okay, here I want to explain the graph here, okay, for the IEEE gain and for the realized gain. You can see here there are two types of efficiency. The first one is the radiation efficiency, okay. If you see the radiation efficiency, suppose I am want to check the efficiency at 2 gigahertz, then you can see it is multiply this vertical column with the 100, okay. And you can see here, if you multiply with 100 you will have 55.06%, okay. So it means your radiation efficiency is 55.06 percent at 2 gigahertz, okay. But if you check the total efficiency at 2 gigahertz, then you can see it is multiply this one with 100 and you will see it is 9.2%, okay. So the total efficiency is 9.2%, okay, because this efficiency include the environment, okay. So it means your antenna is has effect of the environment, or the environment has effect on your antenna, okay. But if you see combined results, then you can see these graphs must be very close to each other, okay. I mean the points, okay. If you want to see like this one, the green one is the total efficiency, okay, and the red one is the radiation efficiency, okay. Suppose if you have designed the antenna at 2 gigahertz, then you need to check this graph, okay. These 2 points must be linked with each other, okay, or can be very close to each other, okay, so that your you will know how much efficient your antenna is efficient, okay. And similarly in the same way you can see here, like at 2 gigahertz, okay. Now you can see here their IEEE gain, realized gain is minus 6.27 dB, while at the gain IEEE gain is 1.5 dB, okay. So you can see this is the gain only of the antenna, but including the environment it is minus 6.27 dB, okay. So in using the FR4 you will have this kind of problems, okay. As I told you, in the real case we are using time domain solver, and this is related to the real case, okay. In the real case you will FR4 will not longer usable, okay. So that's why. Okay, what in antenna we use, we check S parameters, okay. That is the S11, okay. You can see here S11, 11 means the single port, okay, means single input single output, okay. Your antenna works as a transmitter and as a receiver, okay. And you can see the S11 because you are using single port, one port, okay. If you are using two ports, then there will be 4 cases, okay. And keep in your mind, let me explain here. Okay, if you have a single port, okay, then you need to know the relation 2 power 0, okay, 1, Okay, if you are using 2 ports, then you will have you will have 4 relations. Okay, this is with S11. Okay, this is S11, S22, okay, S21 and S12. Okay, this thing. And in this case, this means the scattering parameter of the port 1, this means scattering parameter of the port 2. Okay, and this one means how much effect of the antenna 2 has how much antenna 2 has impact on the antenna 1. Okay, and this one means how much antenna 1 has impact on the antenna 2. Okay, this means coupling technique. Okay, or coupling analysis, mutual coupling analysis. We will discuss in more detail. Okay, when we use MIMO antennas. Okay, recently my one article accepted in IEEE access in MIMO antennas. We will discuss in detail. Okay, the other one is the yes please.
S parameter, we have the two dip point. Can you go back to S parameter?
This one.
S11, yes.
Yes.
Here we have the two peak points.
Yes.
And so what do you say, at which frequency range this antenna has the maximum transmission of electromagnetic waves?
Yes, you can see in ideal case the S11, let me write here, in ideal case the S11 must approaches to minus infinity. Okay, if you have ideal antenna, then it will approach minus infinity. It means if you have more deeper reflection coefficient line, then it means your antenna is perfectly resonating. Okay, rather than you have very close to this one. Okay, minus 10 dB line, this one you can see minus 10 dB line, it is very close to minus 10 dB line. Okay, in practical maybe it will not work at this frequency. Okay, so you must have below minus 10 dB. Okay, and you can see it is minus 22 dB. If it is more deeper, yes,
it's the reflection coefficient. If you go to more deeper, then it means the antenna is resonating very properly.
Yes,
but for the transmission, we don't see this peak point at this peak point, but we check the range of between two peak points, in which
oh, you mean the bandwidth, you mean?
Yeah.
Okay, yes, you can see here you have to check with the sorry, this is 10 dB here. Okay, in order to calculate the bandwidth, you need to curve the markers. Okay, here like this, you need to set at, okay, or maybe you can no, you don't have option. Okay, you can see here the first point, this is the first point. Okay, it is should be at 10. Okay, like this, and the second point is also at 10. Okay, now you need to subtract this one. Okay, 2.63 minus 2.55. Okay, whatever you will get, you can also use here as I told you, there is a calculator here. Yes, this one. Okay, you can calculate here. Okay, 2.6325 minus 2.5539. okay, calculate, and this is how much? 0.0786 gigahertz. Okay, this is in gigahertz because your frequency is in gigahertz. Okay, and in order to calculate in megahertz, then you need to multiply this one with 1000. Okay, and what you will get like this. Okay, and you have 78.6 megahertz frequency bandwidth. Okay, and if you want in percentage, then you need to first you need to you have operated the design at 2.5 gigahertz. Okay, you only have designed at one frequency. Okay, like this range. Okay, then you need to subtract this one. Okay, you need to subtract this frequency and divide by operating frequency, like you have operated this design at 2.6 gigahertz. Okay, 2.6. okay, multiply with 100. Okay, and you can see this is 3.02%. okay, let me write the formula here to calculate the bandwidth. Okay, in order to calculate the bandwidth, okay, you need to f2 minus f1, okay, over operating frequency. Okay, if you want in gigahertz. Okay, but if you want in percentage, then you need to calculate in this way: f2 minus f1 over f resonating frequency multiplied by 100. Okay, then your will be in percentage. Okay,
Actually, I was asking about the antenna working principle between 2.6 gigahertz to 10 gigahertz. In between these two frequency ranges, the curve is on to 0 dB. So what does this mean?
I did not understand what you mean. Can you repeat your question, please?
My question is that from the S parameter between two frequency ranges, like from the 2.6 gigahertz to 5 gigahertz. So we can see the curve is very nearly close to 0 dB.
Yes.
So what does this mean? Here, the band is giving the 100% transmission efficiency.
Look, first if you have curve below minus 10 dB, it means your antenna is only working at one frequency. Okay, like this one. Okay, and you can see here there are two types of reflection coefficient, that is below minus 10 dB. It means your antenna is dual band. Okay, it is working only at two frequencies, one frequency at 2.6 gigahertz, the other frequency at 5 gigahertz. Okay, while at the other frequencies it is transmission is very close to zero. It means it will not work at other frequencies, only it is working at 2.6 and 5 gigahertz. Okay,
Mr. Sarosh,
yes please.
when I get my multiple frequency resonance frequency in
Yes.
this parameter,
Yes.
that's mean that antenna can I use it for this frequency at the same time?
It means your antenna is multi-band. Okay, your antenna is working at multi frequencies. Okay, so it is good thing.
Yes, a multi-frequency.
Yes.
That means I can use it at the same time, this antenna for this frequency.
Yes, you can use, because you can see if your antenna is multi-band, then it means your antenna is working at multi-frequency at the same time.
Okay. So I can use for example Wi-Fi antenna for 2.4 and 5 gigahertz at the same time.
Yes.
I think we can't.
For the Wi-Fi, can you explain your second question, please?
Mr. Ahmed, I mean I can use one antenna for multiple frequency.
Look, you suppose if you have a multi-band antenna, suppose your antenna is working at 2.4 gigahertz and now other frequency is 5.2 gigahertz. Okay, you need to know the applications of the operating band, like at 2.4 gigahertz what operating applications are there. Okay, so you can say at first frequency band your antenna is working for GPS, okay, or global positioning system, or while at the other frequency your antenna is working for WLAN application. Okay, so you can say if you have multi band antenna, then your means your antenna is multifunctional. It is multifunctional. Okay,
and for radiation total and radiation efficiency, when I get the result, when I can say that the result is good.
Yes, if you have as I told you, if these two curves points are very close to each other, then you can say your antenna is good. Okay, or it must have.
What value?
Yes.
What value I should? What is the best value? 0.6 or 0.8?
Look, this is just 0.6 means 60%. Your antenna must have efficiency more than 75%. Okay, so you can see here it will be 0 and it will be 1 here. Okay, it means 100%, 0 to 100%. Okay, and your antenna must have close points, these 2 points, more than 85% or more than 75%. Okay,
for the two radiation.
For the two radiation, yes, I mean this is the total efficiency, this is the radiation efficiency. These 2 points must be close, but it must be greater than 0.75. Okay, means 75%.
Okay, it's clear. Thanks.
Okay. Okay, now if you want, there is some other options. I am just telling you to improve. Wait a minute, there is a question. Okay, we will discuss in more detail coplanar copolarization and cross polarization in circularly polarized. Is there any here or not? Okay, I think there is not here. We will discuss. Okay.
Excuse me, Mr. Sarush, I have questions.
Yes, please.
Can to assign which the part of the patch that radiation, yes, the specific frequency, or the 2.4, which part of that patch that give 2.6 radiation?
Okay, let me explain this one. Okay, so the other thing is that suppose you have seen that your antenna is working at 2.6 gigahertz and other is at 5 gigahertz, but you don't know which part of the patch is working at these frequencies. Okay, so in order to know these things, you need to calculate the surface current, okay, or E field or H field. Okay, so I did not calculate here. So in order to calculate the surface current at at the desired frequency, like at 2.6 and 5 gigahertz, then you need to go to the post process simulation, go to the field monitor. Okay, first you need to calculate the surface current, okay, in H field and surface current. Okay, so you need to write here 2.6 gigahertz, okay, and click apply, and then you need to write 5 gigahertz and click apply, okay, and click OK, and re-simulate this design, and then you will have the surface current and H field, E field for the frequencies of 2.6 gigahertz and 5 gigahertz. Okay, then you can better see the results. Okay, so first let me calculate this. If you will have slots inside, then you will be more easily you can see the surface current. Okay, but this is a simple patch, so let's see how will be the surface current.
If the negative value of S11 is higher, so it means that the reflection is very minimum, right?
The reflection is good. Okay, as I explained earlier, your S11 must be approaches to minus infinity, means it must be deeper, okay, in minus.
And also it means that the reflection is much minimum, because we want the antenna to transmit all the electromagnetic waves, not reflected there, right?
Okay, in MIMO antenna you will more better understand, because the S21, like this one here, like you have S11, okay, and S22 are your reflection coefficient. Okay, your antenna is working as reflection coefficient. Okay, but in the case of S21, or you can say it is transmission. Your antenna is transmitting. Okay, this is transmission coefficient S21. Okay, the simulation is complete now, and you can see here you have called the field monitor for the surface current 2.6 gigahertz. Okay, and you can animate this one. Okay, or you can increase the surface current. Okay, from here, can you see here? Okay, now click on the animate field. Okay, now you can see. Okay, now if you are not able to see, if you can see the red portion in the design, okay, like you can stop the simulation here, or if you want to increase little bit the inner position, you can see here there is a red portion or red surface current in the patch. Okay, or
Yes.
it means your antenna, if you have the red portion, it means you're like at 2.6 gigahertz, because I am checking at 2.6 gigahertz. So it means at 2.6 gigahertz your patch, the middle, this part of the patch is working. Okay,
Yes, thank you.
okay, and for the 5 gigahertz same.
Something to increase the S11 here.
Wait a minute, let me explain this one first. Okay, then you can ask question. Okay, and you can see for the 5 gigahertz frequency, the part of this part of your design is working. Okay, so in this way you can know. And one other thing is that if you suppose, if you create a slot, if you create a small patch here, then it means your frequency that is at 5 gigahertz will shift. Okay, you can shift in this way. Okay, and for the 2.6 gigahertz, if you create a slot inside this patch at this position, then you can vary the lower frequency band. Okay, like 2.6 gigahertz. Yes, now you can ask question.
Can we manipulate this portion to control or to increase the power radiation for the 2.6 in patch, or maybe in the inverse way, maybe they change the connecting between the feed and the patch to increase the width of the line, transmission line, to
Yes.
Reduce the 5 and increase the 2.6.
Yes, there are so many ways, because you see there are many types of the antenna. Okay, and if you increase or decrease the field line, then it will affect your S11 or your results. Okay, so you need to check the efficiency. If you have better efficiency, more than 75%, and the total efficiency and the radiation efficiency points are very close to each other, it means your antenna works very well. Okay, in all conditions. Okay, like power flow and everything. Okay.
Thank you.
Okay, I want to create a slot here. Okay, inside to shift the 2.6 gigahertz frequency. Okay, this one. Okay, if I create slot in the middle of the patch, okay, then your frequency will shift. Okay, so which type of slot I can create, it's up to you. Okay, which type of slot you want. Okay, in order to create a slot inside the patch, you need to shift the this one, WCS at the patch. Okay, now at this point. Okay,
Sorry, Mr. Ahmed.
yes, please.
How to know the position of the slot?
How to know? It's up to you. You can create any type of slot. You can how to know means you need to see the surface current. Okay, you can see here the middle portion of the patch is working for the 2.6 gigahertz. So it means in order to shift the 2.6 frequency band, you need to create a slot at the middle of the patch. Okay, and which type of slot you can it's up to you, which type of slot you want. Okay, but mostly we use horizontal slots, vertical slots, or L shaped slots. Okay,
Okay. So it's depend first on the surface current.
yes. from today, from tomorrow, we will follow the research paper, okay, to start our design like single multi-band, okay. And you can see this is above the patch, okay, so you need to use minus sign, okay. Now you can see this is inside patch. Okay, now you need to delete this one, cut this slot from the patch, click the patch, click minus sign on the keyboard and select the slot and press enter, okay. Or if you want multi slots, then you can use like where is the slot, this slot, okay, and you can make a copy of this slot, okay, like this, click apply, like this, okay, like this, and you can cut out like this. Okay, I will explain one more thing later once this, or let me, okay, let the complete.
Sir.
Yes, please.
Sir, actually, to cut the slot on the patch, we need to check the surface current actually, na? Where we are getting a maximum surface current. At that
Yes.
point, we have to cut the slot actually.
Yes. Right.
Okay. Okay. Thank you.
Negative gain, I told you before, it depends on the efficiency. If you have better efficiency more than 75% or 80%, then you will have positive gain, okay. It is negative gain because of the lower efficiency.
So,
Yes.
what is the effect of this slot in the patch? Like surface current means the current is moving in this conductor like that. But if we do the slots, it means the current is not concentrated on the center of this patch.
Look, you have a field line here, okay. You are exciting the antenna from this point, okay. It means your surface current will flow, your current will flow in this direction, okay. And you can see here, when the current moves here, the current will flow where is the patch, okay, where is the copper, okay. But it depends how much density of the current, okay. If you have multi slots, and maybe it will work at multi frequency, okay, maybe it becomes multi band antenna, okay. Let's see the results, okay. So I use many slots, but if you want to use one slot, then it just shift your frequency, okay. I have used many slots here.
So the first point is that the slots are used to make the multi-band antennas, right?
Yes, it can be, or it can be to set the frequency, okay, or it can be to increase the efficiency, or it can be to increase the or to reduce the size of the antenna, okay. There are many functions of the slots, okay. We will study step by step, okay, when we study these things.
Brother Sarush, I want to tell you something. Actually, to broaden the bandwidth of the antenna, or to increase the bandwidth of antenna, you know, the PCB itself, it has a conductor and a dielectric material, and also there is another conductor. It's something like a capacitor. But if you change the plate of the capacitor, to reduce it. This means that the quality factor, you know,
yes,
it will be changed.
yes, yes,
and we have inverse proportional with the quality factor and the bandwidth.
yes,
yes. For that, if you reduce the size by making more slots, you can broaden the bandwidth, because at this time the quality factor will be reduced.
yes,
the Q factor. Yeah.
Because if the size will be smaller, then it is hard to fabricate the I mean lumped elements like capacitors, resistors, inductors. That's why in most of the cases in reconfigurable antenna we keep the size like this, okay, as we have in this, or maybe smaller, but we do not use in millimeter wave or in in the size less than 5 cross 5 millimeter, okay.
Okay, thank you.
Excuse me, sir. Sir,
yes,
your antenna is resonating on 2 frequencies.
Yes.
So what's the logic behind why it is not resonating on 3 frequencies or 4? Why it is on 2 frequencies?
Okay, it's up to you at which frequency you want, okay. Suppose I want to design the antenna at only to work only at 2.45 gigahertz, okay. Then you need to neglect other frequencies and you need to set the range, okay. Like you need to set the range at 2 gigahertz, from 2 gigahertz to 3 gigahertz, okay. And then if it is working at 2.7 gigahertz, then you can add slots, okay, to set the frequency, or you can reduce the size of the patch, or you can reduce the size of the substrate, okay. You can reduce the size of the width of this field line, or you can decrease the length of the field line, okay. It's up to you, okay. This is the logic behind. And other thing is that I am using full ground plane, okay. If you also have slots in the ground plane, then it will become multi-band, okay. Or if you can use it is not necessary to use the full ground plane, okay. You can use half ground plane, you can use partial ground plane, you can modify the shape of the ground plane, or you can use the CPW plane, okay. I will show you how to design CPW antenna, okay. This is the simple patch antenna, okay. And you can use the ground plane on this side, okay, this side on the right, left side or the right side, okay. In most of the CPW antennas you can get wide bandwidth, okay, like wide ultra wide band or wide band super band, okay, like this. If you will create slot, then it will take more time in simulation.
Excuse me, Sir Sarush.
Yes.
Sometimes when you reduce the ground plane, the radiation feedback
Yes.
from inverses from the patch to the ground, so the feedback radiation increase.
Yes, yes. You mean yes, it happens most of the cases that if you are not using the full ground plane, then your antenna provides back radiation, okay, that may harm your body, or if you are working on the human body antennas. Also in antenna it is not acceptable that you have back radiation, okay. So you need to apply different techniques to control your radiation pattern. Like you can use in antenna arrays, you know, the radiation pattern is most of the cases direction pattern, okay. And in the case of the you can use metamaterial, meta surface, or artificial magnetic conductor to control your radiation pattern, okay. Or you can use CPW technique, okay, in this way. But if you are use half or partial ground plane, then it sometimes gives a back radiation pattern. Okay, you can see here at first it was the reflection coefficient at was this point, okay, 2.6 gigahertz, but now it is shifted back, now it is at 2.13 gigahertz, okay. So you need to check where 2.3 gigahertz, okay, or near the 2 gigahertz. Okay, so it means the edge of the slots are in has contribution at 2 gigahertz, okay. It means if you decrease or increase, if you you can see the width. Okay, let me use dimension. Okay, it is like 3 gigahertz. Okay, suppose. Okay, if you reduce like you can make it 2 gigahertz. Okay, to control this band. Okay, to control this band, or maybe it will work below minus 10 dB. Okay, so you need to use some small patches here, or you can increase or decrease the length or width to control this first frequency band. Okay, okay, the other thing I want to tell you about the, okay, yes, let's know this one. Okay, parametric sweep. Okay, what is parametric sweep? Okay, now let's apply the parametric sweep on the width of the field line. Okay, so it will take more time, so I need to reduce the slots to save our time, because in parametric sweep means it will optimize your design at different samples. Okay, so let's delete so that it will not take more time. Okay, like you have the width of the field line is where is the width? Yes, this one. Okay, you have the width of the field line is 1.5 millimeter. Okay, you want to see what will be the effect of on the field line or on the S11 if you reduce or increase the width or length of the field line. Okay, so you use parametric sweep to do multi simulations. Okay, so you can click on the new sequence, go to the new parameter. Okay, and you want to optimize for the width of the field line. Okay, so you need to select this one, and then you can write here 1 to 2 gigahertz. Okay, so and if you choose 3 samples, okay, it means your antenna first simulate at give you results at 1 gigahertz. Okay, I mean sorry 1 millimeter the width of the field line. Okay, then like this. Okay, you can see here the width of the field line, it will first simulate at 1 millimeter, then second simulation it will be at 1.5 millimeter, and then for 2 millimeter. Okay, then you click on the start, and then it will start simulation like this. Okay, there are three simulation will go run for 3 times. Okay, one for the 1 millimeter, and second simulation for the 1.5 millimeter, and the third simulation will be for 2 millimeter. Okay, so in order to optimize, you can see your width will change. Okay, during the simulation. So you have any other question, or I can stop the simulation if you want, because it may take more time.
So sometimes simulation prolongs and more than it takes more time your expectation, you know.
Yes.
So like in MATLAB you use command control C to abort to come out. So what's that? Does a control C command is applicable in PSP or it's different?
Which type of command you are talking about?
To abort, I mean to stop simulation, like just to give up simulation. So because sometimes it takes a long time.
Yes, you can stop, but where you stop, it will show you the results. Like if I want to stop the simulation here, okay, it will skip the simulation. Or if I want to stop the simulation for the for the 3 simulation, okay, then you can click on it, and you can see whatever the results here you will have. Okay, then it will stop the simulation. Okay, the other thing, the other important thing to know about meshing view. Okay, this is important thing. If you have less number of meshes, then it will simulate very quickly. Okay, and it will not take more time. But if you have a long number of meshes, you can see here it is 1 4 1 2 3 6. Okay, meshes, number of meshes. Okay, so some people ask me how to increase the number of meshes, how to decrease the number of meshes. It is not a proper way. How to, you need to know which mesh size is applicable, or which mesh size is more preferable for this type of patch antenna or for your design. Okay, so in order to select the optimum mesh view, you need to go to the time domain solver, and you can see here adaptive mesh refinement. Okay, it means when you click on this option and click on you can see yes, you need to select this one. Okay, adaptive mesh refinement. Okay, it refine your design at the optimum conditions. Okay, like it will, when you start the simulation, then it will simulate your design maybe for 6 times, maybe for 2 times or 3 times. Okay, it will give you the most optimum results, mean more refined results at the optimum mesh cells. Okay.
Mr. Sarosh.
Yes.
Mr. Sarosh, this problem is in probably in student version.
Yes, this happens in student version.
Yes, because you must change the meshes.
Yes, so you not need to change the mesh. Just go to the setup solver and just click on the adaptive mesh refinement. Okay, it will give you the optimum or best results.
Yes. And can you please enter the port option?
This one?
No, port.
This?
Port 1. Yes. Can you enter?
At this time it is simulation running. You are not able to open. Okay, you can see here.
Yes. I just I want to see one option.
Or if you want, I can reduce. If you want to keep the results until the simulation has done, or you can keep results, click OK, then simulation will stop. Or if you do not want any type of result, just discard results and click OK. Okay, it's up to you. Okay. Yeah.
So
Yes.
Like for meshing question.
Yes.
Sometimes we don't use this adaptive mesh technique.
Yes.
Sometimes we use the manually to set the mesh size around the edges or maybe around the patches of the antenna. How do we do it? Like what's the procedure?
This one you can see, or maybe you can go to the mesh view, or you can also use I think, let me check here, because I do not use this one much. I just click on the adaptive mesh and you can see here.
Yes, you must reduce here.
Yes,
cells.
Yes, you can see here cells per wavelength, and you can set your, it's up to you. Okay, whatever you want.
So what is the default value like for optimum results? If we use the cells per wavelength, how much should be? It should be 10 or 15 is okay.
If you have a more number of meshes, then it means your design will be more refined. Okay, in results. If you have very less mesh cells, then your design may have not good results. Okay.
And sometimes is better to reduce to 7 or 5 to get the result.
Yes, right.
How to calculate this cells per wavelength? Cells with the box of this background, right?
Yes.
To the edge of the patch.
There are some research papers. Okay, there are some formulas to calculate these cells per wavelength and these things. Okay, you can calculate from there. Okay, you need to write your what I mean wavelength, or you need to write the frequency band. Okay, or you need to write the epsilon value of the substrate. Okay, then it will calculate for you. Okay.
Actually, I want to see the cells per wavelength on the edge of the patch. How can we see visually of these cells, not by settings? If we go,
you can see here mesh cells, or there are the total number of mesh cells here. Okay, can you see here?
Yes.
Okay, and also if you are not able to see here, just click on the mesh view. Okay, you can see here mesh cells. Okay, for all the design in the box. Okay, in the radiation box.
we have the large antenna, but we use the symmetry plane. Can you explain about this symmetry plane?
What do you mean by symmetry plane?
Like if we don't want to simulate the whole antenna, we just cut the plane in half and we check the results for one part. So we can assume that the results containing this one half will be symmetrical to the other half.
Yes, you can see this is the half of the results. Okay, so you have 145 728. Okay, and it will be the same for the other side. Okay. Okay.
So as you told about the mesh cells limitation, it depends upon the length, width of the patch and the permittivity on these factors actually.
Yes.
I want to know what are the limitation, what is the maximum, middle or minimum mesh specification usually? I have no idea. Please can you
yes, actually it depends on your frequency, on your size of the design. Okay, because suppose if you are working at a higher frequency and you have very small size of the antenna, okay, then in the simulation results may at a high frequency you will have very small size of the antenna, like at 5 cross 5 millimeter. Okay, that is very small, but you can see here at this design, in this case you have you can see this is one cell. Okay, this is your one cell. Okay, but in the case of if you want to reduce let me use okay, in order to increase the mesh cells, okay, in small designs like of 5 millimeter cross 5 millimeter, then you need to have very more number of mesh cells. Okay, in a very simple or on the surface. Okay, so that's why you need to have more mesh cells to in order to get the most refined results. Okay, there are some research paper I will download and send to you to study. Okay, so maybe you will know better. Okay, let me discuss about this one, lumped elements. Okay, so let's
Can you, Mr. Sarosh, first go to port option?
yes, this.
Why you check in ensure shielding this option? Because by default is not checked.
Where what you are talking about?
About ensure shielding.
Shielding.
Shielding option. This one. Shielding option in the last one.
This one?
Yes. What's the benefit of it?
Okay, I did not click on it, but you can, if you want to.
Because by default is not checked.
Yes, I think it not a problem. Okay, you can simulate it without it. I did not click on it.
Okay, I thought you are checking.
Yes, I did not use it, but you can, if you want, you can use it. Okay.
Excuse me,
Yes.
Mr. Sarush.
Yes.
What's the preferred value for the standing wave ratio?
Yes. No, it is not simulative. Actually, the value of this voltage standing wave ratio should be less than 2. Okay. For if you, yes, it must be less than 2. For ideal case it should be approaches to 0. Okay, approaches to 0 in ideal case.
Thank you very much.
We have the number of modes also. What does this mean, number of modes? Like these are also S parameter.
Wait a minute. Let me. Here you are talking about port modes.
Yeah, I'm talking about port mode.
Yes, it means if you have one port, then it will show you for the port one. Okay, if you have multi ports, then it will show you two ports. Okay. Let us complete the simulation. There are many things to tell you. Now the time is going running. I mean, we have this option. This is very important option to know, and also this one. Okay, and many other options, because these are the basics. If you know these things, then you will understand many things easily. And also in the field monitor. And did you understand these parametric sweep?
Yes, of course.
Okay, and this is a very important thing to know. Let me try. Also, I click on the. Okay.
Mr. Ahmed,
Yes.
Can we reduce the accuracy for simulation, for reduce the time of simulation?
Yes, in the time domain solver, if you when you go to the adaptive mesh environment, go to the properties. Okay, and you can reduce the number of passes. Okay, here I calculated for 6 passes. Okay, so I can reduce the, I mean, I can save these results for the pass one and neglect the other results. Okay, once it complete, I will delete this, stop the simulation.
Yes.
So usually, CST, how many passes have? How many passes?
It's up to you. It's up to you, because in the options you can see mostly because we take up to 4 passes or 5 passes. Okay, that are enough. Okay, but if you want more passes, then you can directly write there. Okay.
Can you show this option, please? It is
Yes.
see the passes.
It is let wait for a minute. Let me complete this simulation. Then you need to go to the time domain solver. Okay.
So meanwhile, can you suggest us about some like if we are designing antenna on particular frequency and to know the basic equations for length, width of patch, substrate, and ground, like?
Yes, I told you before. No, at the moment, no researcher follow any equations, because you see the research paper. Suppose if you calculate the size of the antenna, like you have found that by calculating with equations, you have find the width of the design is 30 millimeter and length of the design at 45 millimeter. Okay, but if you see the research, previous research, you will find more compact size than this size. Okay, then it means they are not using any equations. So you need to you just use these questions to know how much size of the antenna that should operate at the desired frequency band. Okay, so you can use, maybe you can reduce more size than the equations. Okay, to operate your antenna at the desired frequency. So in order to calculate with the equation, I suggest you to read research papers, the previous research papers, and check how much size they have designed. Okay, but I when we read the research paper, then I will show you in the how we can calculate with the equations.
Thank you, sir.
And also there is a schematic option. We will study in the reconfigurable antennas. Okay, like this one.
Sir, Sharu sir.
Yes.
Sir, there is any kind of example you are considering in coming lectures for a leaky wave antenna also in the course or not?
The other topics, on the other topics, maybe I can invite some researchers or some colleagues to have a webinar or seminar or one day seminar, okay. Because we used to have some seminars. I did work on leaky wave. I have a one paper on leaky wave antenna with my friend, but it is better if I invite some more professionals, okay, to have some webinars, seminars.
Okay, sir, just give me some suggestions, sir, regarding like if we are go for a PhD work right now. So in which field recently we are working on antenna basically? That is
yes,
hot topic right now.
because you can see most of the people had done a lot of work on these types of the antenna, okay. So in order to get different ideas, like I am teaching you these types of the antenna so that you are able to, if you combine two fields, 2 to 3 types of the antenna, like you combine metamaterial, reconfigurable, okay, or human body. There are three, you are combining 3 types, then it will become a very good research paper, okay. You can publish target IEEE transaction, okay. But if you are asking, this is the hot topic nowadays, dielectric resonator antennas, okay. You can go on this field, okay. And antennas for underwater communication, okay. And antennas for what we say, vehicular communication, okay. For vehicular communication, it is very hot topic. And also massive MIMO or ultra massive MIMO antennas.
I think for vehicular communication, we are using the frequency selector services, reconfigurable intelligence services.
Yes, it's up to us, or it depends on the results, how results you are getting, okay. Like if you are have problem in the radiation pattern using the vehicular communication, then you can use meta surface, okay, to control your radiation pattern. And you need to do this parametric sweep in your home, okay. And you need to show me the pictures of the results on WhatsApp, okay, so that I may know you have learned this parametric sweep and other things. And also adaptive mesh, okay. Okay, in time domain solver you can see here adaptive properties, and you can select your passes here, okay. Minimum it must be true 2, okay. And maximum you can write here 3 or 4 or 10, it's up to you, okay. And there are so many options here like this, okay. We will study step by step when we learn different antenna types, okay, because we need this option, okay. And also in most of the cases people ask me, is there any option in CST to just take a snap of the picture to get high resolution graph? So in CST there is an option, okay. You can go to the properties, okay, and you can see here you can select the range, like I want a range from 2 to 3. You can write here 2 to 3, click on apply, okay. And you can see here and now if you want to increase the font size, okay, then you can write bold, okay, or you can use time New Roman and click on the 16, and you can see here, okay. And the other thing, if you want to change with the curve style, okay, let me use here, okay, curve style, okay. This is your curve, okay. And you want different color, okay, like blue color, okay. Click apply, you see blue. If you want to increase the line width, you can use 5, okay. You can increase the line width, or if you want to use a dotted line, dash line, you can use, okay, like this.
And what does this mean? The 0D results axis, like x-axis and parameter curve.
Which one you are talking about?
0D result axis.
Here you are talking about?
Yeah. After the Y-Smith chart, there is the option of 0D result axis.
After the Y-Smith chart, you are talking about
next one. Yeah, x-axis and parameter and the curve.
Okay. You are talking about this one.
Yeah.
Okay, we will see it. Okay, let me explain this one. And I think there is a size. Wait a minute. Okay, you can also apply different shapes here. Okay, like you can use diamond shape, you can use square shape. Okay, like this. Okay, and one more important thing to know is that you have seen some research papers, or maybe you have seen some graphs. You use, let me zoom this graph. Okay, now you can see or let me use this solid line so that it is more visible. Okay, like this. Yes, in when you use HFS software, and or maybe you have seen some graphs in research papers, that you will see some dotted or dash in the graphs. Okay, that are very few in line. Okay, but in the CST you have very number of samples. Like you can see there are very number of many number of samples. Okay, so in order to have a graph like this, then you need to reduce the number of what we say samples. Okay, and I think it will be in the simulation. Yes, and it will be option here, go to the specials. Okay, and yes, this one. Okay, if you reduce this number of samples, you will have very you can see in the background there are so many dots. Okay, you can reduce the number of dots. You can write here 50. Okay, to have a graph like that. Okay, so when you do simulation, then you will have, okay, less number of samples, because some graphs looks very good in less samples. Okay, if you have very many number of samples, then it is hard to or the graphs are not very attractive. Okay,
Mr. Ahmed, always we choose 51.
Not 51. It's up to you how many you want. Okay, you can use, maybe you can, it's up to you. In CST you are open to work. Okay, you are not limited to anything. Okay, you can use what you want.
So always we must reduce just the samples.
Yes, only in the case of the in order to plot the graphs. Okay, but if in the case of these results you cannot, because if you reduce the number of the samples, your graph will not be very attractive in simulation, but in professional software may be attractive.
Okay.
Because if you have more number of samples, your graph like this. Okay, like this S11 curve. But if you reduce the number of samples, then it will like this. Okay, it will not be very attractive. Okay, it will like this, like this.
Mr. Sarosh, I want to ask you something. Some papers working in metamaterial, for example, and they designing a cell for metamaterial cell.
Yes.
And they using the same layout or structure.
Yes.
Of CST.
Yes.
And with a high quality. They're using the Visio, I think, to
yes.
make it in high.
Yes, I also use MS Visio, but now it is expired. This is MS Visio. Okay, I use many professional softwares.
Visio, we can take this picture and we can make it with high quality in Visio.
There are two types of designing graphs. Okay, I can explain better in this.
No, I use the Visio, but it take long time.
My Visio is now expired. You.
I mean to export.
Yes.
The layout from CST to Visio and to show high quality. How they make it in the paper?
I actually they use to three ways.
You talked about this yesterday, but I tried long time ago, but the quality of the graph is not good from CST.
Yes, I know. They do not just take picture or paste in the Visio. They design in the Visio itself. Okay, they design a complete antenna in MS Visio. They design the substrate. Okay, because my Visio is expired, I can use MS PowerPoint. Okay, you can also use MS PowerPoint to design high resolution graph. Okay, like you can use. I will explain in the lecture when we have. Okay.
I know how to do it, but they're using for the cell. You know, the metamaterial cell sometimes is very difficult structure. They take the screenshot from CCT
yes.
with a high resolution.
Yes,
how they make it?
I also use in this way. I take snap from the CST, okay, and then I paste in the MS Visio or maybe in MS PowerPoint, and then I use arrows and I create an outline, okay, in the MS Visio. You can see here this outline, okay, so that it is more attractive or more visible.
Also, I want to ask you something, Mr. Sarosh. In some paper, sometimes we saw, sometimes they show the layer of the structure separately. How they make it? The CCT.
They if yes, you can actually it is simulation running. Okay, let me explain here. Like I want to
display the distance between the layer.
Yes.
But I think there is another technique. I think they use it.
Yes. Let me. There are many ways to do it. Okay. You can see they reduce everything. Okay, and they use the white color here. Okay, white color, and you can see like this. You have an outline like this. Okay, or they can also draw this outline in the MS Visio or in MS PowerPoint. Okay, if you do not want from the CST, it's up to you.
No, I don't mean that. I mean sometimes they show the 3D layout in separate layers, the batch layer and the substrate layer and also the ground layer. I don't know how they do it.
They use transform option.
Transform
yes,
option, I tried to use it, but
you are talking about this one. I have done in my papers.
Oh yeah, it has been done in the meta subset. Like we have the 4 layers, the 3 layers.
You mean like this?
Yes.
In my this is done in MS PowerPoint.
Oh.
Yes.
I tried to the transformation as
no, I do not use transformation here. I design this. Yes, I designed this shape in MS PowerPoint. Okay.
I hope if it's possible, you can show us, please.
Actually, it depends on your design. Like you have a design like this. Okay. You need to take a snap, and then you need to create a complete shape on the same figure. Okay. I will explain in the this lecture professional graph tools on Tuesday at 22, because now it's time, it's up to 2 hours now.
Because it's required for us in metamaterial design actually. If you have many layers, yeah. Thank you.
Or you can ask me privately. I will explain you, because now it's time. It's much time now. Okay, and on that day I will explain in more detail. Okay, this session.
Okay, thank you.
Which is better, MS Visio or PowerPoint?
Actually, I prefer to use MS PowerPoint. Okay, because MS Visio is more very good, but the problem is if you have a license, it will expire with the MS Power. It works with the MS Word. Okay, if you design any shape here, then you can directly paste in any word. Okay, and it will not affect your resolution and everything. Okay, but if you have a license, or you can use this. Okay, but you can also use MS Visio and MS PowerPoint are almost the same. Okay.
Okay, thank you.
So
as we got a new result.
on 2.6, we observe that your dip is getting much lower, which is better actually. So what is the factor? How we can go for deep dip of on certain frequency?
Actually, you cannot go more less than minus 50 dB, okay, because in simulation, in my research experience, and also I noticed up to minus 50 dB. You cannot below much minus, actually I suggest you to keep your results in this range, okay. Let me, you can use minus 25 to minus 40 dB, okay, they are acceptable, okay. And also in simulation it is possible, okay. So it's up to you, okay. And it depends on your designing, when we go with the designing process, okay, because in this training course we need to select one design, okay, like when we learn all the designs, okay, all the types of the antenna, then you all of you have to select one design on which you will work and to write a journal, okay. So then I will explain each and everything, because first you need to select one type, and then you need to design a new shape with some novelty. I will guide you everything, okay. Then on that days we will be working on it.
So can you please show US11 return loss graph?
Here it is like this. Actually simulation is not done fully, that's why if you want I can.
Excuse me, Ahmed.
Yes, please.
How to observe the different modes in antenna simulation when we are doing. Can you tell about the modes, different modes?
Which mode you are talking about?
To observe the different mode at different, like we have a different resonant frequency. So how to observe different modes?
I really did not understand your question. It depends, or maybe you are asking about the number of frequency bands, and to observe how can we observe, I mean how can we get or check the first mode to I mean to control the band. You are asking about it?
Yes.
Yes, I as I told you in the surface current, when we are discussing the surface current, you need to check the surface current at the specific frequency band, and then you need to see where the surface current is more red, okay. The red portion you have in the patch, or maybe in the ground, or maybe in the field line, then you need to modify there, okay. You need to, maybe you can add slot there, maybe you can add more small patch there, okay, to control the first band, okay. Then on the other frequency band you need to check again the surface current, and you need to check at which frequency, I mean at which portion of the patch is more red at the other frequency band. Then you need to go there, and you need to do the same procedure as you have done for the first one. So it's up to you. When you are designing the antenna, you are free to do anything, okay. It's up to you. I told you before, in antenna designing you are open to do anything, okay, because in the research, if you see the research, no one is following any equations, okay. They are just simply see how much size have been done in the previous research, and they try to reduce more size than the previous research, and then write papers like this.
Okay, sir.
Right, sir. As you said, as you increase the of the epsilon, your frequency will decrease, right, sir?
What you need to increase?
So when you design a patch antenna, permittivity factor,
yes,
like
yes,
you said,
it is inversely proportional. Yes, it is. Yes, I think I need to write the complete formula here. I think there is a formula. C is equal to f lambda, right? This is the formula, and lambda is equal to c over f. Okay, and there is a one more formula to calculate the guided wavelength. In some papers you will see like this, or maybe you will see like this. Okay, they are guided, you can use this one. Okay, for guided wavelength, because in our dimensions of the antenna are in millimeter. Okay, but in most of the research paper you will see guided wavelength or electrical wavelength. Okay, or electrical size. Okay, they tell only the size of the antenna in guided wavelength. So in order to calculate the guided wavelength or the electrical size, you I think you need to write like this. Okay, so this is the formula to calculate the guided wavelength. Okay, and you can see, notice here, if you do like this, you can replace this one, and you can see this is inversely proportional to each other. I will show you once we read the once we start writing the research paper, then we will do each and everything step by step. Not at the same time we will do everything. We will learn everything. I will try my best to teach you as much as I can. Okay, I don't say I am very expert, but I am trying to deliver all my knowledge that I have.
Sir, thank you, sir. So I just want to know, what is the factor to increase the dip resonant? Is there any factor? It depends on certain length or width of the patch, likewise.
Actually, you in CPW, when we use CPW technique, then in most of the cases we have deeper S11. Okay, when you use the CPW. Okay, like there are very small samples here. Wait a minute. Okay, you notice one thing, that I have reduced the number of the samples. Okay, and you see there are very less samples now, and you see there is one sample here and the other sample is here, and they just connected each other. Okay, if you have less number of samples, and if you have more number of samples, it will be very smooth curve. Okay, okay, if you use the CPW, you see there is a, you need to modify some ground plane. Okay, to get the sharp peak. Okay, I mean sharp S11. You can delete this one, you can use CPW technique. Okay, let me show you what is CPW. There is a ground behind the substrate that is full. Okay, patch antenna, and if you use this CPW technique, then it will become a monopole antenna. Okay, and CPW left. Okay, and you need in this direction, so you can write here width of the CPW. Okay, and you need in the upward direction you need a length of the CPW. Okay, W. Okay, now you need to write TP, thickness of the patch. Okay, and you need to write here, you can write any here, later on you can set the values. Okay, now CPW right, and you need minus width CPW. Okay, and in the upward direction length CPW. Okay, and click TP. Okay, Now you can see the gap between them. Okay, there is a much gap, and in the case of the CPW the gap must be very less, okay, like of 0.2 millimeter. Okay, so you need to reduce the gap. Okay, where is the CPW? Okay, now you need to write okay. In designing you do not get anything in very less time. You need to do so many efforts many times. Okay, okay, now this is your CPW. Okay, why it is called CPW? CPW means co-planar waveguide, the plane at which you have the patch, radiator and the ground plane on the same side of the substrate, then it is called CPW. Okay, and it is very easy and it is very helpful. Okay, to control the frequency band. Okay, if you increase the length you can vary the frequency band. Okay, and if you increase the width then you can vary the impedance. Okay, or you can vary the S11 depth.
Can you see the plot of Smith chart? Like, I think this option I've seen somewhere.
Yes, let me complete the simulation. After you are able to see. In most of the designs I use CPW technique. In many of my designs you can see.
But Mr. Sarusha, how you can dealing with the board?
Yes, for the moment I am just telling you about the CPW, but in this case the port will be dual sided. Okay, I mean it half must be on the other side, half on the other side. Okay, you can calculate with this.
Can be used here, I think. So why we've got board only?
Yes, in the CPW you need to use waveguide port, but if you set at 50 ohm then all results will be the same. I mean yes, you cannot use discrete port in this case. Okay, because
Yes.
you don't have a ground plane on the other side. Okay, that's why you have ground on the both side, so that's why you need to use this one waveguide port.
Sure. Thanks.
So after this I need to end this session. Okay, I need to go to the another class.
How much scholarship are you getting in Italy for master?
Better to ask me privately, not here.
Okay, I will ask because okay, I will ask you probably.
Okay. So everybody know I'm a master student. I'm just started my masters. Okay.
But you've done a great job. Like many papers, you have deep knowledge about the antennas.
I started my research from 2021.
Yeah. So what do you think? How much electromagnetic waves, EMP, and the microwave is much effective in antennas?
Yes.
Because equations, maxwell equations, and other wave equations are very important for the wireless communication. So what do you think is the impact on our antenna designs?
Yes, they have a lot of impact, and you see in our daily life there these are just antennas, but if you study its application, like you have implantable antenna, and why we use implantable antennas for for in-body endoscopy. Okay, you can there are many ways to design implantable antenna, and it is used for biomedical application, and they now doctors feel very ease in order to operate to a patient. Okay, so there are many ways, like also MIMO antennas are using in vehicular communication. Okay, because they have multi ports, and they are
also implantable antenna in fabrication. I think it may be not a big problem, but to found the phantom for human body, or for example the liquid in the human body, it's very difficult, I think.
No, in my lab I did measurements here. In my lab it is available, because in Pakistan actually in implantable antennas you use the human bodies, but in the case of real I mean in fabrication and measurements you can like in to insert this antenna inside human body is not easy as in the practical one. Okay, so you need to find that yes.
I told you about it because I have experience in it before, and the paper is rejected because we try to make a liquid like a stomach, and we make a capsule.
Okay, but my paper is not rejected. My friend recently.
No, it wasn't IEEE the transaction. They said no. Maybe there is a difference between the simulation and maybe the real measurement, because the liquid itself we cannot reach to exactly the same properties of the human body. It is something normal.
No, let me. I will explain once we study this topic. Okay, I will explain how, because you first.
They rejected.
Maybe you have done in different way, but here the epsilon value of the, like in human body cases, if you want to insert this antenna you can insert inside human body, but in practical case you cannot insert inside human body, so you need to use the material that is very close that have very close properties to the human body, like you have a pork material. Pork material is not available in the Arabian countries, but in European country it is available. So it is available here, and we test our antenna inside pork material, and we see there is no much difference in the simulation and measurements, because they are very close to each other. Okay, in terms of epsilon value, relative permittivity. Okay, if you know the relative permittivity, then you can claim that you have very close results, and the results are acceptable.
Sure. Thank you.
Okay,
sir, please show me the Smith chart, sir. Option.
This one.
Yes, sir. Sir, either it is I mean it is allowable range. I mean it is acceptable, or like in VSWR should be between 2 to 1, or like S1 should be below 10 dB. So can you explain this? What information we are getting on this chart?
Okay, wait a minute. Okay, we have two types of charts. One is the Smith chart, and the other one is the Smith chart. Okay, they are just a mirror of the other one. Okay, So we have a dual band antenna, okay, and you can see here there are starting point here. You can see here this is the 0, that is our frequency range is from 0 to 6 gigahertz, okay. You can see here this one, okay, 0 to 6 gigahertz. So it means your Smith chart is starting from 0 gigahertz, where here is 0 gigahertz, and it is ending at this one, okay, here, that is the 6 gigahertz frequency band, okay. So you have you have two types of results here. One at you can use curve markers here, okay. Okay, now you can see if your antenna is resonating at suppose 2.6 gigahertz, then you need to set at 2.6 gigahertz, and you can check the values. Where is 2.6 gigahertz? Okay, suppose this is at 2.6 gigahertz, and you can see the impedance, your impedance at the frequency bands, okay. And also at like you have a dual band antenna, okay, and you can see your impedance at this position, okay, like this is showing at 67.27 ohm, okay. And this is the real part, and this is the imaginary part, okay. Or in the case of voice,
you adjusted the impedance is 50 ohm perhaps.
Yes, that is at the desired frequency band, okay. At the moment you can see our design is not working properly at 2.6 gigahertz, okay. So if it is not working at at the desired frequency band, then it means you have let me check here, it is 50 ohm, yes, but in all you have set this impedance at the desired frequency band, for the desired frequency band, okay. You need to design the antenna. Where is this one? Okay, now you can see if you have a proper results, like you have a good S11 that is below -10 dB and that is much deeper, then you can see it will have impedance exactly or maybe near to the 50 ohm, okay. Or I will try to explain this one, or maybe using the research paper, because in the research paper we can have much knowledge about it, okay, and how we can improve this one, okay.
Suraj, I think we can observe the capacitive and inductive phenomena of the antenna through Smith chart. Like if it is resistive, it means it has the maximum transmission of the electromagnetic waves
Yes.
from this band. But if it is a inductive and conductive, so it can show some the reflection loss, or maybe it can show some the transmission loss.
Yes, I think on the upper part is the capacitive, I think, or the lower part is the inductive, I think. The line,
like
this
that.
one. Yes,
Inductive
this one.
part is always positive, and the capacitive part sometimes we see the negative part.
Yes, and in this case it is more inductive, okay, because most of the portion is lies below this one.
Yeah, because if it's more inductive, then it means it can have the maximum coupling coefficient also, and then for both applications we can do this simulation.
Yes, we will also study about the lumped elements, okay, but not for today, because we are 2 hours and about 22 minutes, so I need to go to the another class, and we can
Okay, sir, just a minute, sir. I just I'm not understanding. It's a game. Please, can you forfeit? Can you go in to see the game polar format, like?
Yes.
You just shown us. So this type of polar plot I've seen in the research paper. They are working on different phases, phi or theta. Like they have this kind of results. So many results available in the papers. Can you just tell what is phi and theta, or like
Okay, we are better able to see in the 3D plane. Okay, let me see. Okay.
In the research paper, they don't use 3D plane. So in the research paper, they use polar plot.
Yes, I mean, I know. Just to explain the phi and theta.
Right, sir.
Okay, you can see here, you have a phi at this point. Okay, this you can see the blue circle. Okay, so it means your phi is this one. Okay, and the red one is your theta. Okay, that is like the red circle. Okay, and in most of the papers they use phi equal to 0 or phi equal to 90. Okay, so you can see you have a design here. Can you see the design? Let me go to transparent mode. Okay, are you able to see design, this design? Can you see this design?
Yes, sir.
Okay.
Yes, sir. Yes,
now you can see the phi and the theta. Okay, now we have where is this one? Yes, this one. The below, the red line is the phi. Okay, oh sorry, yes, the below one is the phi. Okay, you can see phi is working in this plane. Okay, while the theta is the red one. Okay, yes, now this is more visible. Okay, theta is in this direction. Okay, that is you can see 360 degree at your hole and design. Okay, if you see the polar plot, you can see the design here. You can see this is the pod, this is the patch. In you can you are you able to see on the upper side there is a patch and then substrate, and on the lower side there is a oh sorry, this is the CPW ground. Okay, so you have the patch and the ground on the same plane. Okay, so you have a patch, you can see your design, and you have a radiation pattern. Half of the radiation pattern is above the antenna. Okay, so and half of the pattern is below the antenna, so it means your design have a back radiation, this one starting from this point. Okay, let me take a snap and explain it. Okay, now you can see this is your patch. Okay, this is your CPW ground, and this is your port. Okay, and the portion, this one, this is above the antenna. Okay, mean on the front side of the antenna. So this one you can say this is directional pattern. Okay, while this one goes below the antenna, so it means your antenna in this portion is back radiation, producing back radiation. Okay, so you need to reduce this one. Okay, and you need to make your pattern like this. Okay, like this on the upside. Okay, like you have a circle. Okay, and this is the reference line. Okay, you must have the directional pattern on the other side. Okay, on the upper side. And in the case of the you can see your design is in this direction, horizontal. Okay, now when I move to the 0 degree, then you can see, okay, now you can see your design is out of the page. Okay, okay, and you can see port on the other side, and your design is showing a back radiation, much back radiation. Okay, so you need to reduce this one. Okay, because we are using CPW technique. Okay, and there is no ground plane behind the antenna. If you have a full ground plane, then this back radiation will not be like this. Okay, I mean like this. It may show directional radiation pattern. So we in order to reduce this back radiation, we use sometimes we use metamaterial, or we use EBG structure, we use FS frequency selective surface. Okay, or we in also antenna arrays we have directional radiation pattern. Okay,
Sir, this polar plot, actually I'm confusing three things. So theta and phi mean E plane and H plane. Like some in paper I see E plane and H plane, they don't use theta and phi. In some paper they use theta and phi. And in some paper I see they use coplanar and coplanar and like
okay,
cross polarization.
E plane means XY plane, okay, XY plane.
Actually, it depends upon your configuration about the antenna.
Yes, also that's why I told you to check the
antenna in XY.
Yes, but that's why I told you to design the antenna by taking into consideration this axis. If you design antenna in different style, like I design this in vertical plane, okay, but if you design in a horizontal, then it will not match this one, and your results may change, and your radiation pattern will also change. Okay, so E plane means XY plane, okay, like where is the XY plane? This is XY plane, okay, so means this is XY plane, okay. And for H plane it is YZ plane, okay, YZ plane, yes, phi equal to 0.
It depends upon your axis.
So yes, you can write in three ways, okay. You can write either E plane, H plane, you can write either XY plane or YZ plane, or you can either write phi equal to 90, phi is equal to 0.
Popularize it.
What?
Polarization. It's related to the polarization. Cross polarization is another thing.
Yes, yes, I think yes, this is here, I think. When actually here all the results are not showing.
Yes, post processing for this, and you can get it. It's a cross polarization.
Yes, I have a graph to let me check I have here or not. Yes, this one. Okay, now you can see there is a cross polarization. If you have a phi equal to 0, okay, and theta is equal to 90, then you will have cross polarization, okay. And if you have phi is equal to 90 and theta is equal to 0, then you will have co-polarization, okay. So I will send you this picture to keep remember, okay. And in CST I'm not able to show you because here there is a issue, I think. All results are not here, so there are also other options like theta, phi and other things, and you select this phi and write the values like this as in this figure.
Brother Sarouj, about the you know the 2D polar plot, actually it is different from GPWS because you know from the right side it starts from 0 to 30 and the left side 0 to 30. I think it's better to use it from 0 to 2 pi or something like this. It's better.
Yes, in CST I think we can change here in the properties.
Yes.
There is option, I think. Yes, this
I think
one.
it's better to use it, yeah.
Like this you mean?
Yes, 0 to 36, yeah.
Yes. Okay, can we discuss tomorrow the other things, because it's a lot of time and now recording also very long, and I'm not sure whether it is able to upload and how much time it will take, and I have a lot of other works, and we can talk tomorrow. I hope today's discussion has gone out.
Thank you for your time, sir. Thank you, sir.
Okay, thank you very much for joining this session, and I hope this other session will also be very interesting for you.